I'm Jay Laura. I work at USGS Astrogeology in Flagstaff, Arizona, and Abby did a great job introducing this talk. So I spent a little time trying to think about how to present to this group, since it's a machine learning and space physics group. And at first I thought, all right, let's just like PSDI, ARD, let's load up on the acronyms because that'll be awesome at 9 a.m. And then I kind of went to the plain language version that we should just make planetary spatial data easier to find and use for people and teams that don't partner with flight mission teams. That's a common sentiment that you'll hear outside of the conference hall, just having dinner. And then I decided to clean that up a little bit and just essentially assert that there's significant domain knowledge that's required to safely and effectively use planetary data for analysis. And this domain knowledge impedes the widespread use of data by experts in other domains, this domain being one example. Planetary spatial data infrastructures and analysis-ready data are possible pairings to reduce the barrier for entry. So then, it's early in the morning as I'm getting this put together, and I'm like, is this just me who is thinking this? And so I went back to a couple different sources just to confirm, like, okay, I'm not just kind of living in my own echo chamber. And as Abby indicated, the NASA PDIRB did a great job articulating in here one particular finding about barriers for data access and data use, and that they have particularly strong impacts on the development and use of machine learning, artificial intelligence methods. If you are interested, there's links down there at the bottom, and the entirety of that 611 is good reading that I think supports that previous thesis. Another example, because I did serve on that group, is the Mapping and Planetary Spatial Data Infrastructure Team, or the MAPSIT roadmap, which has said that spatial data are not readily interpretable to users outside mission science teams, or they're processed in ways that are non-standard. So these are a couple sources essentially asserting that these data, while publicly available, are challenging to be able to use. This then is an area of particular interest for me. And so the question arises then, how potentially could you start to address these? And so here are some ideas. We need data that a non-specialist that can begin to work with. You shouldn't need to be a part of a mission team to be able to work with the data. We need data that are discoverable for both people and machines. And so I think that's well encapsulated by the FAIR data principles. We need data linking and rich metadata to improve data discoverability. The volumes and the heterogeneity of data are impediments, even if you know in general what you're looking for, to be able to drill down and find specifics. All of this needs some kind of glue to hold it together then, and we need to identify and use existing standards, preferably terrestrially tested standards, to be able to support this discoverability. And then one of, hopefully my contributions to the planetary science field is saying, oh man, we really need some organizational framework so that we all know what other groups and other teams are doing, so that we can take these data sets that are challenging to process, have them processed by experts, and not have to duplicate those efforts. So we need some organizational group or organizational framework. What then is planetary spatial data infrastructure as an idea? And then what are individual planetary spatial data infrastructures, the plural form? PSDIs are just simply organizational tools. And from one perspective, they coordinate data suppliers. So those are producers that create data, stewards or custodians that ensure that the data are long-lived, and integrators that pull data from disparate sources and get them collected. They're coordinating those folks to ensure that the data are discoverable, accessible, and usable. Those are kind of the three tenets for making sure that we have data that is well suited for our end science users to be able to dig in and start to use immediately. PSDIs, it's really exciting. They write policies to ensure continuity. And they also adopt defined standards. So they say, these are the standards we are going to use within the PSDI to make sure that the user data interface is as low friction as possible, and that the data tool creator interface is as low friction as possible. The goal of a PSDI, honestly, is for that most users, they're transparent 99% of the time. The data are just working. You're not aware of all of the organizational infrastructure that's happening in the background to ensure that the data are just working. A quick aside that may be of interest, Ross Beyer and I recently wrote a paper talking about generating a knowledge inventory of foundational data products within planetary spatial data infrastructures. And so we identified 150 plus data products that are necessary for the highest spatial efficacy science. These are data products that are widely used across the planetary sciences. I should caveat this, my focus is primarily on solid bodies in the solar system. So this work is focusing on solid bodies. Examples of these are absolutely controlled orthomosaics, geodetic coordinate reference frames as defined by the IAU, elevation or topography data such as low to high resolution digital terrain models. If you're at all interested in any of these, we have a website that's just coming online now, fdp.astrogeology.usgs.gov, where there's a full enumeration of all of these. We're building this out as a living resource for the broader community to help link research scientists with existing foundational data products that we think are of exceptional high value and we know are of high spatial efficacy or have defined and declared spatial errors. We'll talk in a little bit about why those things are important. So that other key component, I said PSDI plus analysis ready data can potentially address this problem. I wanted to run through an example of two different paradigms for data discovery and use. So paradigm A is the paradigm that I would suggest is happening now, where we search or browse some data repository. Frequently in my field, it's the planetary, PDS, the Planetary Data System. In some of this space weather and space science fields, I suspect that there's another node. I don't know exactly. I'm very solid body focused. We download the raw data from those repositories. So far, so good. Then we learn how do I go about processing and use these data. And here's where I suggest that there are dragons. There's significant issues here. For solid bodies, we're worried about radiometric calibration, photometric correction, geometric correction, or photogrammetric control, instrument-specific corrections, so it could be dark current correction or systematic noise removal. If you're working with high-rise data, you're doing CCD stitching. If you're working with CTX data or high-rise data, potentially you're doing some spacecraft dejittering. You could be doing band co-registration in a multi or hyperspectral instrument. Then you are likely map projecting, mosaicing, and post-processing in order to have a product that you are ready to start to use. You're then probably worried, are there any other little bits of domain knowledge that I should have about these data, any specifics? And then the big PS to that is there's a limited set of non-trivial tools that you're going to need to learn to be able to apply all of these previous steps. So you've made it, you have processed these data, you have learned how to pre-process these data, then you process them, and then science happens. So that's kind of our current acquisition paradigm. Analysis-ready data comes out of the terrestrial literature, and it's essentially data that are pre-processed and pre-packaged so that the user spends less time processing the data. So all that expertise that was previously required is replaced by a different knowledge domain that you need to be aware of. So option B is discovery of analysis-ready data. The discovery process is largely similar. You search or browse a data repository or a clearinghouse. Just like with the PDS, hopefully it has rich metadata to support easier discovery. You then download the process data. So again, we're largely synonymous. Then here's a pretty significant difference, I would argue. You need to learn what are these data usable for. So metadata, hopefully, are describing things like spatial error reporting. How accurate vertically and horizontally are you? If the data is attributed, how accurate are those attributes? Hopefully, the data is also reporting fitness for use, a qualitative description. What are these data used for? And so here you're having to ask yourself the question, what can I safely use these data for? Is my method a variation on previous approaches that are fit for use? what do I need to know when using these data? Notice though that this is not a data processing requirement. This isn't learning new tools. This is interpretation and analysis of metadata to determine if it's in your error tolerance for your analysis. And then science can happen. These data are analysis ready, which means they're in common formats, such as cloud optimized geotips, and ready for ingestion into your tools. So if you work in Jupyter notebooks, these should just work with off-the-shelf tools. If you're a GIS person and you use QGIS or ArcGIS, these should just work. If you're doing multi and hyperspectral data analysis in ENVI, again, these should just work. And so it's a different data access paradigm. So at USGS, we've been starting to work on this. And so I wanted to take an opportunity in this talk to just identify and promote that we have some analysis ready data available now. We're working hard this year and hopefully in future years to make more analysis ready data available. We have a browser, which is screenshot above here. The URL is in the slide where you can see our lunar, Martian, and Jovian analysis ready data sets. The lunar one is very small. We're just starting to get data pushed. For Mars, we have some really interesting looking CTX digital terrain models, which are all set to go into your favorite analysis tools. We should be releasing 1,000 to 2,000 more of those this year. And then for Jupiter, we have some Europa data, photogrammetrically controlled image mosaics, individual images that are really interesting for doing stuff like change detection or image classification and segmentation. And then we should be releasing a handful of digital terrain models as well. There's also some tutorials. Again, these are being built out right now about accessing these data via the command line. We should have another one coming live in the next few days about accessing via Jupyter notebooks. And then to me, this is exceptionally important. We have an API for discovery. And so I think that that is high value to the community to be able to write against these data stores, this data clearinghouse to be able to access data. What makes this work? Previously, I talked about standards. The Spatio-Temporal Asset Catalog is seeing wide adoption terrestrially. We've been working with that team. They are absolutely amazing to modify the specification sufficiently that it will support planetary bodies. This is a machine learning first specification. So it's coming out of Radiant Earth and Planet Labs, who are companies that are supporting data discovery and use for machine learning applications. There are two interesting there's three interesting extensions. One is our planetary extension, I think, but the other two are extensions for labeling and for model provenance tracking. And so it would be exceptionally interesting to see how those extensions can be integrated into some of our analysis ready data. I'll talk about that a little bit below. This screenshot is essentially just browser rendered. It is, in my mind, a fancy FTP site. Here's a big list of data. We'll provide you some thumbnails. We'll give you lots of metadata. The real power, I think, comes from that previously linked application programming interface, that API, to be able to do some machine-driven work on large data sets. So what right now are we working on? And we is a broad community. It's USGS, it's MAPSIT, the NASA advisory group that focuses on a lot on spatial data, PSDI governance group. So there's a Europa PSDI that is working hard. And we're currently in this fiscal year doing the easy stuff. We're making more data available. So Europa DTMs should have about 140,000 Kaguya terrain camera images released. We should have the entirety of the Themis controlled data set released this calendar year. And then we're writing lots and lots of documentation, because in addition to releasing the data, it's that documentation component that's going to make it very usable. We're also beginning work on some of this hard stuff. The semantic and non-semantic data linking is exceptionally important to be able to find or drive users to, users being people or machines, to other common data sets that may be of value in analyses. We're working on increased and improved metadata with a strong push towards improving discoverability of data. When you have 140,000 Kaguya trained camera images, simply drawing your bounding box and saying, give me everything in here is nice, but it can be exceptionally overwhelming. We need some improved discovery tools. We're also starting to think about ways to ingest new and derived products. So people are applying machine learning algorithms to data sets in order to generate new derived data sets. We need a method to be able to then take those data sets and pull them back into these analysis-ready clearinghouses so that we can serve them to the community and start a really healthy feedback loop. So I spent a little time thinking, like, how does this relate to this group specifically? And I think that there's two ways. First is as a service to the planetary machine learning community, which is to say we're working to make machine and human discoverable data in common interoperable formats with metadata, and that includes provenance, so you can understand or reproduce exactly how the data was made for you in this current form. Freely available so that you can apply whatever science or perform any science that you might want to do. I think there's a lot of opportunity to partner with the machine learning community. So making that data available is awesome, but there are many machine learning techniques that would be valuable to apply and then re-ingest into this ecosystem. So that could be ARD, analysis ready data fusion, object detection and classification for metadata, image segmentation for improved metadata, new product derivation. So recently I've seen some very interesting lunar examples performing image enhancement using, I think, CNNs, but I'm not exactly sure. Any type of change detection is of big interest for missions, particularly mapping missions where we have good repeat coverage. And then machine learning for image registration, I know is a thing. I have like a whole bunch of questions about it, but potentially there's big value there. And hopefully I didn't talk to New Jersey fast, and I think I should be good on time. So any questions or discussion, I'd be happy to answer.